So here we go. We are now moving into arguably the toughest part of this course, and that is talking about a buffer. Today we're just going to do a little qualitative stuff, and if you get today's stuff, I guarantee that when you have to do these calculations, you'll be good to go. All right, first of all, you need to know what a buffer is. It's a solution that is designed to resist changes in pH when a strong acid or base is added to it. This would be quite helpful. Your body has a number of buffer systems. If you assail it with a strong acid or a strong base, I think most of the time a person who has diabetes, if they have an insulin problem, they can go into ketoacidosis, and that change in pH could be lethal to their blood chemistry were it not for the fact that there's a buffer system that's designed to keep the blood pH pretty much at 7.41. 7.5, you're not doing well. 7.3, you're not doing well. So a buffer is a solution that resists the change in pH when a strong acid or base is added. How does it do that? It takes care of the invading strong acid or strong base. So there are two parts of a buffer, and a buffer can only consist of a weak acid and its salt, and remember the salt would be a conjugate base, or a weak base and its salt, a conjugate acid. All right, so what you cannot have is a strong acid and its conjugate base. Here is the acid, here is the conjugate base. Why can't you have a strong acid and the conjugate base? Because a conjugate base is too weak to defend against a strong acid or a strong base being added. So the question that you have to determine is whether an acid-base duo can function as a buffer. So here we go. We have this. Do you see a weak acid or a weak base? Which one? Okay, here we go. This is a weak acid. And when we do a Bronsted-Lowry thing to see what its conjugate would be, if this is the acid, that means it needs to give up a proton. And when it gives up a proton, it would look like this. So here's the conjugate base. Here's the acid. This is the conjugate base. I don't get what that K is doing there.
It's the salt.
It's the salt. Very nice. Okay, and if you would look at this when it was hydrolyzed, remember when we did that? This came from this and this. Okay, so yes, indeed, this is the conjugate base. It should work as a buffer system. Got it? All I heard was some grunting. That's not a good thing. Yes or no would be great.
Yes.
Okay, here we go. I need you to identify whether you see a weak acid or weak base. You see this strong acid, which is perchloric. So the strong acid is going to produce a weak conjugate that's too weak to defend, so this will not make a good buffer system. Now, looking for a strong, a weak acid or a weak base. Yes or no?
No. Or yeah, yes.
It's a weak base.
The weak base is, okay,
Well, it's a
and
weak.
that's a weak base.
Conjugate acid.
And its conjugate acid would be NH4+, which is fairly strong. Okay, and OH minus. So, yes, this does work.
I'm confused.
Why?
It didn't, I don't see what the salt is,
Yeah, where's the salt?
This would be the salt part.
just because it gained an ion.
Okay, here, if I did this, would you be okay? If I make it, I'm sorry, if I wrote this, here's the salt. Okay, here, I know what this is bothering you. You can think of it as a weak acid and its salt, okay, if it has this on there. Or you can think of it a weak acid and its conjugate base. All right, these are actually the same thing, but if it helps you recognize, I only see the conjugate base. In this one, all you saw was the weak base and its conjugate. In this one, you saw the weak acid and its salt.
So
Either one of those are good to go.
And why is the weak base on top on that one?
Okay, it just is. I'm going to give you a direction in one moment that we're going to set these up the same way every time. It doesn't really matter what's on top or what's on the bottom, as long as you can recognize it. When we go to solve problems, it absolutely positively matters, and we're going to set them up the same way. If you deviate from the way that I tell you to set them up, it will not work out for you. So you're going to have to really just do what I say. This can get really complex, and I'm going to take a derivation of an equation and have you use it the same way every single time. So follow along, do what I do. Okay, in order for a buffer system to work, the buffer system itself, this is what the buffer system would be, the weak acid and its salt, or if you're thinking about it, the weak acid and its conjugate base, or the weak base and its conjugate acid, or the weak base and its salt, has to be in much greater concentration than the invader, than what is going into it. What that means is you need an overwhelming amount of buffer to take care of a relatively small amount of strong acid or strong base. Pure water has absolutely no buffering capacity. So if you add a strong acid to water, that strong acid is going to dissociate completely, and that hydrogen ion is going to greatly affect the pH. So if you had a pH of 7 when you had the strong, when you had the neutral water, you added a strong acid, let's say it was 0.1 molar, the pH would then go to 1, negative log of 0.1. So it would really change the pH. 1 molar would hurt if it got dropped on you. So water has no buffering capacity. If you threw in one of these, it would work to resist the change in pH. The pH would go down some, but not as greatly as it would as if the buffer was absent. So don't be scared. These are just variations of the common ion problems. This is step 2 of what you really wanted to know, what you need to know. So the first thing you needed to know is to be able to identify, is this a buffer? And the thing you're looking for is a weak acid or base and its conjugate or salt. Now, the second thing that you absolutely have to know is how a buffer works and the particulars on how it protects the solution's pH from the invaders. Okay, this is kind of like a war situation. The buffer are the defenders, and the strong acid and the strong base are invading the beaker. All right, so here we go, and I always want from now on, your buffer system is always set up this way. Acid over base. So if it's written in another form, I need you to change it around so acid is on top, base on the bottom. Really, look, it's just like in the alphabet. A comes over B. All right, acid over base. Okay. Does this act as a buffer? Yes, it does. This HPO3 is a weak acid, and this is its conjugate base. We're good to go. Now, you need to know how to write a reaction that will show how this buffer system will change when you add a strong acid or a strong base. Okay, let's say we added HCl. It's a strong acid. The only thing that's going to change the pH is the hydrogen ion. And we want to see what happens. You're going to have to choose, is it the acid or the base that protects the solution from a change in pH? Well, here, I'm going to tell you what happens. If you add acid, base buffers.
Oh, so you could have a buffer system that works, but you add OH to that system and it won't protect it?
No, something else will happen.
Oh,
Hang on.
okay.
So if, get it? Not like that little alliteration, right for your benefit. If you add acid, base buffers.
And
So
H.
add acid, that means base is buffering, it's defending. The base portion of your buffer is going to defend. So here you go. Here in your reactant side right here, you got the war happening right in your beaker. And then the products will be the other part of the buffer system. So you will have one portion of your buffer decrease in concentration and one portion of your buffer system increase in concentration. So you can see from this reaction that your acid concentration increases and your base concentration will decrease. Anybody got a question there?
So it's decreasing because
It got used up. Okay, if we're thinking about that war scenario again, it was a hero and died for the cause. Okay, so it is now out of the system. So if we had, let's say this was 5 molar and 5 molar, and so we think of these as 5,000 soldiers and 5,000 soldiers. Some of these soldiers became heroes, and so there are fewer soldiers left.
became heroes.
They
What if
were
there's-
brave.
What if there's more acid than there is?
Okay, just like in a war, if you had too much of the strong acid, it overruns the buffer system, and the battle is lost. Okay. All right. Now, the other side of this equation is what happens if a strong base is added to this buffer system. Okay, you add a strong base, the acid makes water. Okay. Base becomes water. Add base, make water. Add base, make water. So here we go. We have the strong base. You can see that a proton will be lost by the weak acid, leaving the conjugate base and more water. So in this situation, the acid concentration will decrease and the conjugate base will increase. All right. I personally would memorize this and know that the opposite is the other portion of the buffer system. Here we go. Now we have a conjugate acid over our weak base. It's a buffer system. We still have the acid over the base. And to it, we're going to add a hydrogen ion. Add acid. Base buffers. add acid-base buffers, so we're going to add the acid, and the base is what's going to help out here. The base is the NH3, it's on the bottom, and what we are left with is the conjugate acid. So looking at this, the conjugate acid will increase and the base will decrease. All right, now we're going to add the strong base, and we know that what we're going to end with is some more water, so that will be the conjugate acid making water, and the other product is more base. So this will decrease while this will increase. If you have the way this changes straight in your mind, the next 2 days will just be following directions. This will be no big deal to you. If you don't have it straight in your mind yet, why, look, here are 4 practice buffer systems for you to work with. That's what we're going to do now. These are already pen casted and on the website. So when you get home tomorrow and you say, I don't get this, it's still there. So let's work on these together.